Welcome back. I'm going to resume doing review problems for exam 3, fall 2020. So here's a problem, integrating with respect to arc length. And I include in that, I include finding the arc length of a curve. Integrating a function with respect to arc length is just a more general problem. I'll find the arc length of this curve. I'll rewrite x as 4/3 t to the 1, t to the 1/2, or 4/3 t to the 3/2, so I can take its derivative. Please don't use the product rule on t square root of t, because it's complicated and you probably mess up and get it wrong if you do it that way. So I'll rewrite the parametric equations as a vector function. You get r(t) is 4/3 t to the 3/2 2t1. So the velocity is, see, 4/3 times 3/2 is 2 t to the 1/2. Oh, I'm sorry, getting ahead of myself there. When I wrote out r(t), I was taking derivatives prematurely. R prime of t is 2t to the 1/2, 2t1, and the speed or length of r prime of t is square root of 4t plus 4t squared plus 1. Now I've got to integrate that to find the arc length, and integrating the square root of a quadratic function in general is hard. So let's see if I can make it easier. The radicand factors as 2t plus 1 squared. So if you take its square root, you get 2t plus 1. So the speed is 2t plus 1. That's what we integrate from 1 to 3. That integral is a piece of cake. 12 minus 2 is 10. So the final answer is 10. It's an arc length, so it has to be positive. Unfortunately, we got a positive answer. Okay. The next problem is to integrate 1/2z plus 1 over the same curve. So for ds, I have 2t plus 1 dt. Sorry, t goes from 1 to 3, not 1 to 1. Okay. Now, in the 2z plus 1, I replace z with t, because z equals t. If there were any y's, I would replace them with t squared. If there were any x's, I'd replace them with 4/3 t to the 3/2. Now the integrand simplifies to the constant 1. See, almost as if it were concocted just to do that. Funny. And we end up, the final answer is 2. Okay. Here's some problems of finding vector functions for parametric surfaces. Not doing any calculus on them, just parametrizing them. So it's a good idea to make a sketch. A half cylinder x squared plus z squared equals 4. So the radius is 2. C is non-negative, so we just get the top half. and y goes from 0 to 3. Okay, so y goes from 0 to 3 of the top half of the cylinder. Let's see. So if I look at this from the left, okay, from the left, x goes to the right and z goes up, and I see the top half of a circle with radius 2. So I'll let x equal 2 cosine v, y equals 2 sine v. Well, this is not polar coordinates because the radius is always the same. Y doesn't depend on x or z at all, so I'll just set y equal to the other variable. V is the angle, which goes from 0 to pi. Use the radius. No, use not the radius. Use the y value, which goes from 0 to 3. And I'll convert the parametric equations to a vector function and get r of u v equals 2 cosine v right, 2 cosine v u sine v. Now, it is possible to do that problem without using sines or cosines, but it's a bad idea. It's a really bad idea. One reason is if you have to do something with this surface, like integrate over it, and you have garbage like square root of 4 minus z squared or something, the derivatives are real messy. And so please use sines and cosines. Next, the part of a plane that's inside the circular cylinder, x squared plus z squared equals 1. So it's a flat surface. It's a part of a plane that's inside a cylinder. It's not cylindrical. So I'll sketch that cylinder. Call the surface S. So this surface you can describe as a tilted ellipse, a tilted elliptical region. Oh, wait a minute, that's the wrong cylinder, isn't it? Yeah, the cylinder wraps around the x-axis. So if I sketch the front view, looking at it from the front, y goes to the right and z goes up. what we see is a disk. So I'll use polar coordinates for y and z. And this time it's genuine polar coordinates because the radius varies. Now this time x does depend on y and z. I need to take the plane equation and solve it for x. When I do that, I'll get 4 minus y minus 4z all over 4. And then I have to replace y with u cosine v and z with u sine v. So those are parametric equations. I'll put them in a vector. U is the radius, which goes from 0 to 1. V is the angle, which goes in a complete circle. So V goes from 0 to 2 pi. Okay. Next, let's do some integrating over surfaces. So take a surface and find a double integral for its area, but not do the double integral, and then also integrate a function over that surface. So to calculate surface area, we have to integrate length of RU cross RV. Oh, and it would have been nice if I'd given the intervals for U and V. Let's let U go from 0 to 1 and V go from 0 to 2. Sorry about that. Okay, so gotta find RU cross RV. RU is 1, 1, V. RV is 1, negative 1, U. That turns out to be U plus V, V minus U, 2. I find the length of that vector the usual way. Length of RU cross RV simplifies to radical 2u squared plus 2v squared plus 4. So the answer to the first part is integral as u goes from 0 to 1, v goes from 0 to 2, or square root of 2u squared plus 2v squared plus 4. Now this is probably possible to do exactly. It would be a really ugly trig substitution problem followed by another really ugly trig substitution problem. Unfortunately, no one is asking us to do that. Now the second part is to integrate a function over that surface, and I chose the functions to get something we could actually integrate. So we get to recycle all our work from above. ds is square root of 2u squared plus 2v squared plus 4. Now in the integrand, wherever there's an x, we replace it with u plus v. Wherever there's a y, we replace it with u minus v. And if there were any z's, we would replace each z with uv. Now, when you algebra this, the denominator turns out to be radical 2u squared plus 2v squared plus 4. And wow, what a coincidence. That's the same thing as the square root that we had already. So the integrand simplifies to 1. Final answer is 2. And the answer is positive, and even without doing anything, we could have predicted a positive answer, because the integrand is the principal, is the square root of a positive number. If you integrate a positive function, you'll get a positive answer. Okay, here's an example of changing variables in a double integral. And I will give you the change of variables if there's a problem like this. So don't worry about having to find it. Apologize, it looked like this problem got cut off a little bit. It's a good idea to sketch the region. So y is between x squared and 27x squared, and also between yikes. So y equals 27x squared, y equals x squared. Y is also between 1 over x and 8 over x. So we get a 4-sided figure. Erase some of the stuff I don't need. The first thing I'm going to do is find the region in the XY plane that this comes from. I mean in the UV plane. And to do that, I need to find out where the boundary comes from, the boundary of the set. Now this set has 4 sides. So for each of those curves, I'll find out, I'll convert it from y's and x's to u's and v's. I'll start with y equals 27x squared. Sorry, I discovered a mistake here with the change of variables. Should be x equals v over u, y equals uv squared. I fixed it. Sorry about that. So one side has equation y equals 27x squared. I'll replace y with uv squared. And x with v over u. So uv squared equals 27 v squared over u squared. I'm going to do what I tell you not to do all the time, which is divide both sides by v squared. And you can do that in this kind of problem. It can be, there's a way to justify it. But You end up getting u cubed equals 27. So u is 3. Something similar happens with y equals x squared. You end up getting u equals 1. One of the other sides is y equals 8 over x. I don't like fractions, so I'll rewrite that as xy equals 8. And replace the x with b over u, and y with ub squared. I get b cubed equals 8, so b equals 2. You do something similar with y equals 1 over x, you get b equals 1. So u goes from 1 to 3, and b goes from 1 to 2. So in the UV plane, the domain is nice rectangle. Okay, next I'll find the Jacobian. Please remember the Jacobian. It's a serious mistake if you don't. Okay, that's a determinant of xu, xv, yu, yv. Xu is negative u to the minus 2v. Xv is u to the minus 1. Yu is v squared. Yv is 2uv. The Jacobian works out to be negative 3u to the minus 1v, or negative 3v over u. Now I'm ready to write down the double integral. U goes from 1 to 3, v goes from 1 to 2. Integrand is 1 over x squared. That's 1 over v over u squared. I have to multiply by the absolute value of the Jacobian. Integrand simplifies to u squared over v squared times 3v over u. And which further simplifies to 3u over v. And this integral is a piece of cake. So hopefully I can do it. And the integral turns out to be 12 natural log 2. Well, we can do a reality check on this answer. We got a positive answer because 2 is bigger than 1. And the integrand is positive. So we could have predicted a positive answer. And now if I had forgotten to take the absolute value of the Jacobian, I would have gotten a negative answer. Next, I'll sketch a vector field. The vector field 0, 1 minus x. I should write scale. I use one grid line as 1 unit. Let's see. If x is 1, then we get the 0 vector. She draws a dot. If x is 2, we get the vector minus j. If x is 0, we get the vector j. If x is 3, we get minus 2j. If x is negative 1, we get the vector 2j, and so forth. I think you get the idea. Now, notice that this vector field creates a clockwise rotation, and very soon we're going to learn how to calculate its curl. The curl is negative because it creates a clockwise rotation. Okay, next so-called work line integral. I may have a little deja vu here because this is the same curve that I used in the previous example. So we can recycle some of our work. Now we need to calculate this, we need to find integral of f of r.t dot r prime of t. Now the curve is given in parametric equations, so we should convert it to a vector function, just like I did before. So for f of r of t, wherever there's an x, I replace it with 4/3 t to the 3/2. Wherever there's a y, I replace it with t squared. So f of r of t is f of r of t is 9/2 times 4/3 t to the 3/2 0 3t squared. R prime of t turned out to be 2t to the 1/2 2t1. And when you do the dot product, 3 times 2 is 6, 6 times 2 is 12. 12t squared plus 0 plus 3t squared. It simplifies to 15t squared. That gives us 5t cubed, evaluated at 3 and 1. I think that turns out to be 130. By the way, this vector field is not conservative, so we couldn't have used the FTLI. Speaking of the FTLI, there's a problem in it, and I should have written here that I forgot to write that big F is conservative. You don't have to waste time testing or not testing whether it's conservative, because that's given. You can evaluate a work line integral using the fundamental theorem of line integrals. I'll sketch the curve, and the only reason I'm sketching the curve is to I can see, so I can see what the endpoints are. So x equals cosine y. Y goes from 0 to pi over 2. So the cosine of 0 is 1. Cosine of pi over 2 is 0. Okay, so that's what our curve looks like. It starts at 1, 0 and ends at 0 pi over 2. Oops. So what we have to do is find a potential function, a little f, plug in the endpoints and subtract. And since the curve goes from 1, 0 to 0 pi over 2, we take little f of 0 pi over 2 minus little f of 1, 0. Just like if an interval goes from a to b, you take f of b minus f of a. Now here, little f is a potential for f, which means gradient of f is big F. The components of gradient of f are fx and fy. I set the I components equal and get fx equals e to the x plus cosine y. Set the j components equal, get fy equals 1 minus x sine y. Top equation, f is integral with respect to x of fx. And when I integrate, I get e to the x plus x cosine y plus a constant of integration. And that constant of integration might have y's in it. So I'll call it g of y. Do the similar thing with fy. F equals integral with respect to y of fy. Just integral with respect to y of 1 minus x sine y. That's y plus x cosine y plus h of x. So this time, the constant of integration might have x's in it, so I call it h of x. I have two different versions of f of xy, and they're both f of xy, so they have to equal each other. So f of xy equals e to the x plus x cosine y plus g of y. And it also equals y plus x cosine y plus h of x. That equation simplifies to e to the x plus g of y equals y plus h of x. I'll separate variables and get g of y minus y equals h of x minus e to the x. Now the left is a function of y alone. The right is a function of x alone. And the only way they can always be equal is if both are constants. So I'll set them equal to my favorite constant in the whole world, which is 0. And then I can solve for, say, g of y and get g of y equals y. I plug that back up there and conclude that f of xy equals e to the x plus x cosine y let me write this out. But e to the x plus y plus x cosine y. Now it feels like I'm done, and that's a great feeling, but I'm not quite done. I have to use the potential function, and I have to plug in the endpoints. I'm going to rewrite the potential function up there with the help of the old short-term memory. So f of xy is e to the x plus x cosine y plus 1. Okay, I'll plug in the endpoints. I plug in 0 pi over 2, get e to the 0 plus 0 plus, sorry, that potential should end with plus y. So f of 0 pi over 2 is e to the 0 plus 0 plus pi over 2. F of 1, 0 is e to the 1 plus cosine 0 plus 0. That's 1 plus pi, well, I got to write it down. 1 plus pi over 2 minus e plus 1. And that simplifies to pi over 2 minus e. And that's the final answer.